By Professor Minsoo. Her research focuses on hardware-software co-design for system architectures and particularly for ML applications. Okay.
Okay, hello everyone, I'm Jin Kim from KAIST. Today I'm going to talk about ElasticRec, a microservice-based model serving architecture, enabling elastic resource scaling for recommendation models. This work was conducted with my colleague Choi and Professor Minsoo. Recommendation models are used to suggest products or contents to users. And these models are crucial workload in data centers, accounting for up to 70% of total AI cycles in some companies. Therefore, reducing their deployment cost is important for decreasing the total cost of ownership in data centers. Before going into the details of ElasticRec, let's review the typical architecture of recommendation models. They usually consist of embedding layers and MLP layers. When processing a user request, embedding factors in the embedding tables are sparsely scattered according to the features of a specific item and user. The gathered embedding factors are aggregated and passed to the MLP layers, which predicts the user's preference for that item. As embedding tables contain the features of a vast amount of items and users, embedding layers in large-scale services often reach tens to hundreds of gigabytes. This high memory footprint significantly increases the deployment cost of recommendation models. Now I'll discuss how recommendation models are deployed in the current ML deployment system. In the deployment of ML models, a cluster resource manager such as Kubernetes is utilized, and it allocates resources based on the amount of user requests. Therefore, when a large number of queries need to be processed, the resource manager replicates the model parameters, allowing each model replica to process queries in parallel. Current deployment systems leverage this query-level parallelism to handle a large volume of user requests. However, we have identified that scaling resources at the granularity of the entire model leads to inefficiencies in case of recommendation models. First, we identify the inefficiency from the distinct characteristics of dense and sparse layers. Here, the graph shows the measured throughput of each layer. As you can see, there is a significant disparity in the throughput between dense and sparse layers. Such throughput differences pose challenges when deploying recommendation models. Let's see with an example. Let's assume that the dense layer can process 50 queries per second, and the sparse layer can process 100 queries per second. Under this assumption, if 100 queries arrive within a second, the dense layer becomes the bottleneck. Then the current deployment system will create a total of 2 replicas of the entire model to handle 100 queries. However, for the sparse layer, just 1 replica will be sufficient. Here we observe that resources for sparse layers are unnecessarily over-provisioned. Since the sparse layer accounts for the most of the recommendation model's memory consumption, replicating the entire model leads to excessive allocation to these memory-intensive components. Another challenge of model-wise allocation comes from the embedding layers in memory access patterns. These graphs are the access frequency of each item in 3 different data sets sorted by access frequency. As you can see, accesses are concentrated on specific items. In fact, over 90% of accesses are within just 10% of the items. Even though only a minority of vectors are hot, the entire embedding table, including cold vectors, are over-provisioned when using model-wise allocation, which results in a waste of resources. To address these inefficiencies, we proposed ElasticRec, a framework that enables fine-grained resource management and elastic resource scaling. The traditional model-wise allocation can be visualized as this figure. In this method, the entire model acts as a single resource management unit. Consequently, when a large number of user requests are received, all model parameters are replicated. ElasticRec addresses challenges of model-wise allocation by adopting microservice-based model deployment. This method divides a large resource management unit into smaller components, allowing for fine-grained resource allocation based on actual demand. This enables ElasticRec to significantly reduce the deployment cost of recommendation models. Now I will explain how ElasticRec uses microservice-based model serving. First, we address the heterogeneity challenge by separating the dense and sparse layers. In this approach, each model shard is placed in a separate container, and they communicate using networks such as RPC protocols. Since containers can act as the resource management unit of resource managers, placing each layer in a separate container enables independent resource allocation for each model shard. Therefore, if a particular layer becomes the bottleneck, the design allows for increasing resources specifically for that shard. Furthermore, since traffic and computation are concentrated on specific vectors, ElasticRec divides the embedding table into multiple shards. By partitioning the embedding table, more resources can be allocated to half vectors and less to quarter vectors. Such a fine-grained division enables elastic resource management according to the actual resource demand. Now let's see how ElasticRec shares a recommendation model. While separating sparse and dense layer is straightforward, partitioning the embedding table is not trivial. So, to shard the embedding table, ElasticRec first sorts the embedding vectors by access frequency, and then it partitions the sorted embedding table. This method groups embedding vectors with similar access frequencies into the same shard. When we partition the embedding table, we need to determine the number of shards and their respective sizes. In this figure, the example partitioning plan has 2 shards with 3 and 20 embedding vectors in each shard. When choosing these partitioning parameters, you face a crucial question. How can we find the best partitioning plan among the various partitioning options? To choose the best partitioning plan that has the least memory consumption, we need to estimate and compare the runtime memory requirements of each partitioning plan. First, let's take a look at how ElasticRec estimates the memory consumption for a partitioning plan. The total memory consumption of a partitioning plan is the sum of the memory consumption of each shard. And the memory consumption of a shard can be obtained by multiplying its size by the number of replicas of that shard. Since we know the number of vectors in the shard, we can easily calculate the size. Next, the remaining task is to predict the number of replicas that will be deployed at runtime. To predict the number of replicas, ElasticRec calculates the load on the shard using probability density function of vector access frequency, and then estimate the required replicas based on profiling data. Through this process, ElasticRec is able to estimate the total memory cost of a partitioning plan. Now that we can estimate the memory cost of each partitioning option, we need to find the best one among all possible partitioning options. However, as there can be millions to billions of embedding vectors in a table, it is impractical to employ non-exhaustive search. ElasticRec tackles this challenge with a dynamic programming-based table partitioning algorithm. Although I'm not going to the details of the algorithm, the point is that it can effectively reduce the search cost by narrowing down the search space and reducing computation with memorization. Finally, let's look at the overall process of ElasticRec. First, the deployment cost estimator and the table partitioning module decide how to partition the embedding table. Based on the determined partitioning plan, the deployment module generates deployment information. This information is handed to the Kubernetes cluster. At runtime, each shard scales elastically according to the actual user demand, following the deployment policy generated by the deployment module. Through this process, ElasticRec enables fine-grained elastic resource management. Now let's take a look at how well ElasticRec reduces the deployment cost of a recommendation model. We assess the effectiveness of ElasticRec on both CPU-only and CPU-GPU clusters. Note that as ElasticRec can independently allocate resources to each shard based on each shard's hardware affinity, it is inherently adaptable to heterogeneous hardware platforms. Because their results show the similar trend, today I will only show you the result from the CPU-GPU environment. This graph shows the memory usage of model-wise allocation and ElasticRec when serving identical traffic requests without SLA violations for 3 different models. Compared to model-wise allocation, ElasticRec reduces memory consumption by 3 times through its fine-grained resource allocation. Next, I present the results showing how memory efficiency has improved. Memory utility is the metric showing how well the allocated memory is utilized. For this experiment, we measured the percentage of embedding factors that were actually accessed when 1,000 queries were sent. The memory utility of each shard is measured separately. Thus, in this graph, hot shards have lower shard IDs and cold shards have higher shard IDs. The graph shows that unnecessarily replicated cold factors leads to low memory utility under model-wise allocation. In contrast, ElasticRec demonstrates high memory utility for hot shard, as it is designed to partition shards based on their access frequency. The novelty of ElasticRec is its adaptive allocation of resources based on actual resource demand. The yellow diamond marks indicate how many replicas were created for each shard during deployment. As you can see, ElasticRec can successfully allocate more replicas for a shard with higher utility, resulting in 8 times higher overall memory utility. Lastly, we examined how effective ElasticRec is at reducing actual deployment cost. The graph shows the number of servers required to handle the same traffic without SLA violations. ElasticRec used 1.4 times fewer servers compared to model-wise allocation. In conclusion, ElasticRec achieves the elastic resource scaling with fine-grained resource management. Overall, ElasticRec substantially reduces memory usage and deployment cost of recommendation models. Thank you for listening to my presentation. I will be happy to answer any questions.
We have time for a couple of questions.
Thank you. Hi, I'm Fyodor from Microsoft. I have a question about the partitioning of the embedding space or the embedding table itself. How stable is the load on those individual shards? And what happens if you have load shifts? Does that require repartitioning to kind of realize some of the savings you talked about?
You mean in the runtime?
Yeah.
Yeah. How? Yes. Yes, that's a great question. Thank you for asking me. Yes, as you said, the traffic of user requests can be changed as time goes, and ElasticRec can firstly elastically scale the resources, and the memory access patterns are changed very large. The ElasticRec partitions the embedding table again periodically as the access pattern changes.
Makes sense. Thank you.
Okay.
Any other questions? I had one question.
Yeah.
So, what is do you also optimize for batch size and so on in terms of the locality that's involved? Do you also optimize for the batch size of
Batch
requests?
size?
Yeah, based on locality issues and so on.
Yeah, we didn't consider the batch size dynamically, and we measured the performance of one batch size, and gathering the vectors in a batch size.
Let's thank the speaker. Is going to be given by Chen, who is from Macau, right? Wish we are all there.
This one is the laser.
His talk is titled Derm, SLA-aware resource management for highly dynamic microservices.
Good afternoon, everyone. My name is Chen. I'm from University of Macau. I'm very happy to share our work with you. It's Derm resource management for highly dynamic microservices. Nowadays, microarchitecture has gained immense popularity in building a wide range of latency-sensitive online service with exception flexibility. Unlike monolithic architecture, this new approach breaks down complex applications into multi-loosely coupled components, simplifies their management, maintenance, and updates. Consequently, when confronted with heavy loads or resource bottlenecks, microservice architecture enables independent and fungible resource scaling of individual components. Additionally, the scale of complexity of microservice, The scale of complexity of microservices are continuously increasing. For example, by 2021, the Raniwala application has scaled to over 20,000 microservices. Within this application framework, how to effectively utilization resource has become a popular topic in recent years. Service providers often over-provision resource to ensure service quality and handle peak loads or resource contention with other collocated tasks. This results in a very low utilization of microservice application. Therefore, guarantee the tail end-to-end latency meets service-level agreement, while in inference, the resource utilization has become a core focus of the microservice scheduling. However, achieving this goal is quite challenging. When the service receives user request, it starts from the entry microservices and involves a series of sequential and parallel calls to the downstream microservices. This goal graph formed by application requests may involve over 1,000 microservices. Meanwhile, applications shared by different services. Moreover, the end-to-end latency of microservice graph except sequential variability often makes this problem much harder. Existing work has made effort to optimize resource allocation for microservice application by deep learning or explicit modeling. However, all these works do not exhibit high dynamic microservice graphs. The left figure shows that the same application can generate diverse microservice graphs depending on the specific it handles. This application is an example from the training benchmarks, but in the production environment, this phenomenon is even more obvious. Trace analysis from Alibaba cluster, as depicted in the right figure, shows that over 15% of applications contain at least 2 types of graphs. Moreover, about 10% of applications can form 5 distinct graphs, and these applications are typically more popular than others. In microservice application, it's important to guarantee the tail end-to-end latency to meet SLA, not only the average latency. Also, requests sharing the same microservice graph can have widely different end-to-end latency because of the unpredictability in handling user requests. This means that the 95th percentile latency is typically several times higher than the 15th percentile latency. Now, consider the high dynamic nature, such gaps tend to be even more bigger. But these gaps also bring opportunity to improve resource efficiencies. Let's look at the simple illustration. To ensure the application meets the SLA, we could treat every graph equally, which means this would require more resource for a complex graph. However, each graph doesn't have the same likelihood of being called. From the Alibaba trees, we found that graphs with complex topologies are generally called less often. So if we consider the call distribution, assuming complex graphs are called 10% of the time, then we can tighten the SLA for simpler graphs, like meeting the SLA at the 97th percentile. Then the complex graph only need to meet the 77th percentile. By doing so, we can still guarantee the tail latency in application level, but we can consume fewer resources. In order to illustrate this idea, we perform a simple experiment utilizing the tree ticket application with two graphs under fixed load. The ratio between the two different Microservice graphs is about 9:1. We ensure SLA meets the application level, then allocate varying number of containers, configuration different percentage of user requests that meet the SLA for both types of graphs. The top figure shows the resource requirement under different scenarios for different graphs, while the bottom figure shows the total resource needed. The optimal resource allocation occurred with a simpler graph meets the SLA at the 97th percentile, resulting in a 20% reduction in resource usage. This example considers only two types of Microservice graph. As graph dynamic becomes more complex, intentionally allocating optimal percentage to different graphs can lead to even greater efficiency in environment. Determining the optimal percentage is quite difficult, as the distribution of Microservice graph frequently changes at runtime. To calculate graph dynamic, we conduct many experiments and analysis, ultimately identify two key factors that originate this dynamic. First, application nodes can significantly influence the Microservice graph dynamic. We conduct an experiment on Microservice application called Train Ticket Reservation to take the resource requirement for meeting a fixed SLA under different loads. Typically, application need more resource to meet the SLA requirement as the load increased. However, in this figure, we can see when the load exceeds 30 requests per second, the required resource allocation decreased significantly. This reduction is due to the simplification of execution logic caused by the insufficient tickets remains. We also analyze trees from Alibaba cluster and revolves that 95% of applications show a positive correlation between graph dynamic and loads. Meanwhile, the nearly 18% of applications display a strong correlations. Another reason are arguments of user requests. This is more intuitive as it directly impacts Microservice execution logic. Difference in this experiment come from the very number of interstation between different train sets. Derm mainly consists of 5 components. We use latency profiling model to capture the highly uncertainty of Microservice latency, and this latency distribution are utilized to quantify the end-to-end latency. We then use graph dynamic learning and prediction module to learn and predict the distribution of all Microservice graphs. Then, based on this module, we design our algorithm to find the optimal resource allocation scheme. Our Microservice latency is computed by subtracting the response time of all downstream microservices from its own response time to eliminate the impact of upstream and downstream dependencies. The corresponding cumulative distribution function can be well represented by exponential function, referring to the experiments conducted on both the benchmarks and the Alibaba cluster. And the parameter can model as a linear function with respect to the node. This can be expanded by the Q serial. The detail is in our paper. After modeling the latency of each microservices, we introduce how Derm quantify end-to-end performance. Many approaches simply add up the latency of each microservice to obtain the end-to-end latencies, which is clear that efficiency is measured. In contrast, Derm considers both sequential and parallel execution to combine the latency distribution of all microservice graphs within a graph to construct a probabilistic model of end-to-end performance by a convolution operation. And the final equation of end-to-end latency can be rewritten as this, combined with the exponential function. As explained before, the dynamic of microservice graphs are heavily influenced by the application nodes and the specific character of request arguments. So this dynamic within microservice graph naturally exhibits temporal patterns during runtime. So when utilizing historical data and the distribution of request argument and the microservice graph along with the loads to learn this dynamic. After collecting time series sequential of this feature with a specific time window, we use them to train an encoder module based on LSTM with attention, which could predict the graph distribution of next time slope. Now, let me briefly introduce the basic optimization model of Derm. Derm only forces the weight of end-to-end latency between all graphs to meet SLA, instead of requiring all microservice graphs to independently satisfy a SLA requirement. So the constraint can be rewritten as this formulation. Then we solve this optimization problem to schedule optimal resource to each microservice. Now for the experiment setup, evaluate Derm by employment two widely used open source microservice benchmark along with trees from Taobao application. Our cluster contains 10 two-socket physical hosts, and each microservice container is configured with the same configuration. We evaluate Derm by both static and dynamic loads with a range of SLA. The training overhead is quite low. Specifically, the latency profile model for each microservices can be trained with 0.1 seconds, and the graph learning module can be fully trained in 10 minutes. We compared the performance of Derm against the state-of-the-art solutions, including Sriraman, Kraken, and Firm. Derm's prediction can reach a high accuracy, which is enough for resource management. Moreover, accuracy of graph dynamic projection have an impact on resource allocation. We quantify the accuracy for the graph distribution by KL divergency. A KL divergency of 0.2 may lead to an over-allocation of resource over 100%. As for the end-to-end performance, Derm achieve impressive resource receiving. Compare this method which doesn't consider the graph dynamic. Now you may consider whether this non-uniform algorithm might lead to a decline in service quality for users of complex graphs. So we examine the 99 tail latency as shown in this figure. The 99 tail latency remains within twice of the value of 95 across various loads. This indicates that Derm can control the tail latency within an acceptable range for dynamic application. We also simulated dynamic loads based on load trees from Alibaba trees to evaluate Derm's performance in environment which is closer to the real-world production. It turns out that Derm can dynamically schedule resource under varying nodes, consistently meets the SO requirement while saving up to 16% more resource compared to other schemes on average. As a scalability, Derm's profiling can seamlessly scale and deploy with a large-scale cluster. Okay. And the Derm scaling overhead is minimal, and the container setup time before execution can take from seconds to minutes in compression. So in conclusion, Derm is the first effort to optimize resource allocation for microservices with highly dynamic graphs while ensuring service quality and meeting SLA. That's all my presentation. Thank you for your listening.
We have time for maybe one question. No.
Hey, I'm Theodore from Microsoft. I was wondering, to get that like 60% reduction in resources, what were the SLAs like in terms of the percentage of, I don't know, I guess it's different per microservice, but like queries that need to meet a certain standard? Were you looking like 95, 99, 99.9?
So what's your concern?
I'm curious, what did they look like to get that 60% savings number? Were there 95, or were they really close to like the tail?
Oh, you mean the SLA requirement?
Yeah.
It's mostly dependent on the service producer or the user. It's not dependent on ourselves. We just based on this requirement to do our schedule.
So what did they look like according to the users?
We often let the 95 percentile latency to meet the SLA requirement. It's a common requirement.
Okay, so quick follow-up question. If that increased to like closer to the tail, like 99 or 99.9, would the savings increase if you try to kind of hack the SLA the way you did, or decrease?
Sorry.
I suggest, why don't you take it offline if you don't have the answer ready?
Yeah, we can chat later too, if the time is tight.
You mean this?
Let's just chat offline with the
Okay.
next presenter can come.
Let's thank the speaker. The next speaker has the privilege of presenting two papers in the same session, right? We're happy to have Jovan Stojkovic from CMU, who's going to present the paper SmartOClock, Workload, and Risk-Aware Overclocking in the Cloud.
Hello everyone, I'm Jovan. I'm a fourth-year PhD student at UIUC, and today I will present you the work that I did with Microsoft, which is SmartOClock, Workload, and Risk-Aware Overclocking in the cloud. Cloud services are heavily over-provisioned. As cloud applications are typically user-facing workloads, they follow a diurnal pattern. This means that most of the time we have low load with occasional load spikes. In this figure, we take 3 large Microsoft services and we show their CPU utilization over 1 day. These services collectively use 1 million of virtual cores. We can see that most of the time, these services have very low load. However, eventually they have very short load spikes. These services are user-facing applications. They have very stringent service level objective or SLO requirements. This means that we need to provision such services for their peak load. Thus, during the regular load hours, these resources will be heavily underutilized. This significantly increases the cost for service providers and is a major waste in the cloud. Techniques such as auto-scaling and on-demand provisioning are not the remedy for this challenge. First, they have long response time compared to the short spikes in our load, and also they cannot be used for stateful services. In contrast, in this work, we explore the use of overclocking to address this challenge. With overclocking, we want to provision our services for their regular load, and only during the load spikes, we want to overclock or execute our components at very high frequencies, even beyond turbo boost, and improve the performance while saving the provisioning cost. However, overclocking does not come for free. It increases the power of our servers, it increases the component wear out, which means that it will reduce the server lifetime, and importantly, it is opportunistic. Hardware vendors will not include overclocking when provisioning for lifetime, and cloud providers will not include overclocking when provisioning the power. Then arises the question, how can we use the overclocking while managing the associated risks? To answer this question, in this work we start by performing a tower characterization of the environment. Based on our insights, we propose SmartOClock, the first overclocking management scheme specifically designed for cloud environments. We evaluate SmartOClock on a real 36-server overclockable cluster using production workloads. So let's first see what are the main challenges and opportunities for overclocking in the cloud. To be able to efficiently use overclocking, we need to respond to 4 main questions. First, when is it beneficial for the workloads to be overclocked? Second, do we have enough resources such as power and lifetime headroom in the cloud to be overclocked? Then, how can we overclock without exceeding these limits? And finally, if we exceed the limits, how should we act? We first observed that overclocking opaque box virtual machines is inefficient. We take open source Desktop Bench microservices and execute them in 2 environments. One is baseline, which is turbo boost, and the other one is overclocked. We can see that overclocking can reduce the tail latency of both services. However, for the text service, overclocking is not even needed because even the baseline is already within the SLO. However, if we use workload agnostic signals such as CPU utilization, that will lead to suboptimal decisions. We can see that both services have the same CPU utilization, while one is violating the SLO, the other is within the SLO. Thus, if we use such information to decide when to overclock and when not, we will either miss the deadlines or we will inefficiently use the overclocking cycles. Thus, we need a workload-aware signal to enable efficient overclocking. Second, we check how many resources, such as power and lifetime, we have available for overclocking across Azure Fleet. We analyze power consumption of Azure Fleet and observe that it typically has low power utilization, such as 60%. However, it can spike up to 99%. In this figure, we illustrate a typical power consumption of a rack in Azure, and we show that power limit with the red line. You can see that the power utilization is always below its limit, and we can use this headroom between the utilization and the limit to overclock and increase the power without hitting power limits. However, if we naively overclock all the time, all the cores, we will frequently go above the limit, which will cause power capping events. On power capping events, we need to reduce the frequency of all cores in our server, therefore reducing the performance of our services. Thus, we have enough headroom for overclocking in the cloud. However, naively overclocking all the time can cause power capping events, negatively impacting the performance. Similarly, we analyze the CPU utilization of Azure Fleet, and we use TCMC reliability model to learn how many resources, how much lifetime we have to consume for overclocking. Here, in this plot, we show a typical CPU utilization of a server over a period of 5 days. If we assume that this server will be used for 100% utilization, for 5 days, the expected aging is also to be 5 days. However, due to low utilization of servers, using the reliability model, we observe that this server will only age for 2 days. This leaves us with 3 days that we can use for overclocking without impacting the lifetime of our server. However, if we naively overclock all the time, we will increase the consumption of our lifetime and we will significantly reduce the lifetime of the server. Thus, we need a smart overclocking scheme that can take these overclocking cycles that are available for our lifetime headroom. However, we cannot exceed the expected aging. Thus, we have enough headroom due to the low utilization of the servers, but if we naively overclock all the time, we can cause premature server wear out. Finally, how can we know when is it safe and when is it not safe to overclock? For that, we realize that rack power consumption across Azure, along with the other resource utilizations, is very periodic. So we can use the periodicity to predict how much and when we have enough available resources to allow safe overclocking. In the case that our prediction was wrong, we need to go below the limits and we need to perform still power capping events. With conventional systems, they split the resources of a rack across all the servers in a homogeneous manner. However, this is a mismatch between the actual usage of our servers. Here, we show the power utilization of 6 servers that are shared on the same rack over time. So you can see that all servers have very different needs which change over time. Thus, we need to split the power budget on power capping events according to the individual service needs. To address all these challenges, we propose SmartOClock. SmartOClock is the first overclocking management scheme specifically designed for cloud platforms. It uses 3 main components. First, it uses workload intelligence monitor and workload intelligence agents that will collect the metrics of interest and overclock only when the service needs to be overclocked. Therefore, we can efficiently use the precious overclocking cycles without causing premature wear out nor power capping events. Then, we use a server overclocking agent that will decide when is it safe to overclock without impacting the power and lifetime. Finally, we can use a global overclocking agent that will periodically collect the information from all the servers and decide how to dynamically split the power utilization, power limits across the servers in the rack. So let's now go into each of these in detail. First, SmartOClock uses workload intelligent overclocking. With every virtual machine or VM in our system, we deploy also workload intelligence monitor. The monitor will collect the metrics of interest, such as tail latency in the case of microservices, and only when the tail latency is about to exceed the service level objective, the workload intelligence monitor will try to overclock the cores. Once the load reduces and therefore the tail latency goes down, the workload intelligence monitor will see that there is no need for overclocking anymore and it will stop overclocking the cores. In this way, we can efficiently use overclocking cycles while meeting the performance requirements of our services. Second, SmartOClock uses prediction-based overclocking admission. When Workload Intelligence Monitor wants to overclock the cores of its VM, it first needs to check whether it is safe to overclock in that time. To do that, it contacts the server overclocking agent. The server overclocking agent will take the overclocking request and use the power and lifetime model to assess what is the impact of this request on the power and reliability of our system. If there are enough local resources, the server overclocking agent will grant the request. Otherwise, this request will be rejected. Only those requests that are allowed by the server overclocking agent will cause the cores to run at high frequencies. In this way, we can satisfy overclocking requests without causing power capping events and without degrading the lifetime of our server. Third, SmartOClock uses heterogeneous power budgeting. Every server overclocking agent will periodically send its information about the utilization to the global overclocking agent. Such information includes the overclocking and power template, which means how many cores need to be overclocked over time and what is a typical power utilization over time for a given server. The global agent will then compute what is the required overclocking budget for each individual server and forward that information. Then, servers would need to conform to their locally assigned budgets, which are different across servers, to meet these heterogeneous needs. Finally, SmartOClock uses decentralized budget enforcement. Every server overclocking agent is assigned its own power budget. It needs to ensure that the local load needs to be below the power limit. However, it can happen that some servers are way below their assigned budget, while other servers are operating on the budget while still having ongoing overclocking requests. To adjust to that, server overclocking agent starts gradually increasing the frequency and trying to overclock more cores until it reaches the point that the global agent sends a warning message. Such message means that we are about to reach the power capping event, so stop overclocking. In that case, the server agent will go back to the previously explored safe power limit, which is higher than the initially assigned limit by the global agent. In this way, we can maximize the overclocking success rate without triggering power capping events. We evaluate our system by using 2 racks with 36 overclockable servers. We mimic the power consumption of a production rack in its servers by using latency-critical microservices and machine learning batch workload. We compare 4 different systems. First, we use baseline that has turbo boost frequency and fixed number of VMs. Then we have scale-out system that is using, again, turbo boost frequency, but scales up and down the number of VMs based on the load. We have scale-up system, which operates in overclock frequency, but a fixed number of VMs. And finally, we evaluate our SmartOClock proposal. We can see that SmartOClock is able to reduce the tail latency of microservices. Compared to all systems, SmartOClock has the lowest tail latency. Compared to the baseline, scale-out, and scale-up, we can reduce the tail latency by 19, 11, and 9% respectively. Simultaneously, by using less VMs for service, we can reduce the cost for our applications. We can see here the cost for scale-out and for the SmartOClock system. It reduces the cost of applications by 30%. Similarly, by using less resources, SmartOClock is able to reduce the total energy consumption of our cluster. We can see here that compared to scale-out baseline, which is state of the practice, SmartOClock is able to reduce the energy consumption by 10%. Finally, we perform experiments with production workloads. Here, you can see the CPU utilization y-axis over time, it is shown on x-axis for the baseline and SmartOClock system. We can see here that SmartOClock can reduce the peak utilization of our production services by 16%. This directly translates to the cost of production workload. To conclude, we observe that overclocking has lots of potential for cloud workloads. However, it does not come for free. To address all the challenges, we propose SmartOClock, the first overclocking management scheme specifically designed for cloud platforms. SmartOClock is able to reduce the tail latency, cost, and energy consumption compared to state-of-the-practice systems. In the paper, we also share lessons from production, such as how can we use the first-party workloads on experimental hardware, and how can we gauge hardware vendors to further improve overclocking. With that, thank you for your attention, and I will be happy to answer any question.
We have time for a couple of questions. Actually.
What would you do in the case of, how would you get that workload intelligence signal in the case of a black box VM running in the cloud when you might not even know what the SLO is?
Correct. So we assume that we already extend the existing auto-scaling systems. So as, for example, now you can use the auto-scaling system to decide when to create new VMs based on the, for example, tail latency. So we can extend the interface to use for overclocking. So it will just be another threshold in the existing systems.
Sounds good. Thanks.
Yes.
Hi, I'm Jinsun Yu from Georgia Tech. Thanks for the talk. My question is, from 3.3 gigahertz to 4 gigahertz, how quickly can you execute the overclocking? And is regarding cloud workloads which show microbursts at a very short time span, how nimbly are you able to react to those kind of work?
Correct. So hardware changes require in hardware, changing the frequency requires only a few microseconds. However, the software overheads of core changes will be higher. So if we want to reduce this, we also need to have some sophisticated scheduling system that will schedule those requests that need overclocking scheme on cores that are already overclocked. In our evaluations, we use microservices with microsecond and millisecond tail latencies, and we still see the potentials even without going into improved scheduling. However, if we want to get even more in performance, we can go and improve that area as well.
Any other questions?
One more. Sorry.
Thank you.
Steve from Virginia Tech. Just a quick question on the practicality and just reliability implication for overclocking. For example, if you overclock the CPUs beyond the manufacturer specification, would that essentially void the warranty? So that's one question. And then when you overclock, would that cause some crashes and then or some sort of burnout? I know the crashes won't be common, right? But still, in data centers, you're talking about 3 nines or 5 nines of availability. These overclock-induced errors. How do you see them, and how do you deal with them?
Yes, to answer your first question, which is whether the overclocking is covered by hardware vendors' warranty, no. So that's why we say it is opportunistic. We need to make sure that we use some reliability model so that we can go and use overclocking without reducing the lifetime budget, which is specified by the vendors. And the second question, which is whether we see the errors. In our experiments, we didn't see any errors. In the paper, we discussed more about silent data errors and how we can deal with them, either with the current systems or with the future hardware support.
Just following from the first question.
Can we take it offline? Okay.
Thank you.
Let's thank Johan. I'm sorry for introducing you. Okay, anyway, Johan is going to be back for the next talk. We next have Wang, who's a PhD candidate at CMU, advised by Professor Sriraman. Jalen's research spans the system stack, bridging computer architecture to software systems, and he's particularly interested in sustainable data centers. His research has been recognized by several fellowships: NSF Graduate Research Fellowship, Ford Foundation Pre-Doc Fellowship, Benjamin Garver Westinghouse Fellowship, and Jack and Mildred Bowers Scholarship. So he's very passionate about sustainability, and hopefully he's going to tell us, how sustainable we can be.
All right, great. Thank you. Oh. All right. Okay. Sorry? Good? Okay. So before I start, I'd like to ask everyone in the audience to take a seat if you agree that lowering the carbon emissions of cloud computing is important. Okay, clearly you all agree with me, right? Except for you, so I guess we'll have to talk later. But with that, I'm even more excited to present to you today how significantly greener clouds are possible with green server design. And so this is some work I've done in collaboration with Microsoft Azure, where our motivation is that cloud computing has a carbon conundrum, in that the emissions of major cloud providers, such as Microsoft, have been on the rise. And this is a mismatch for achieving their crucial yet quickly approaching net zero goals. And it's been reported that this rise primarily stems from the increasing need for more data centers. And so what this points out is the critical fact that cloud demand is growing, but its carbon reductions are not keeping pace. So then where do emissions come from within the cloud? We find that emissions come from two types. The first being operational emissions, which are those generated to power the hardware within the data center. The second subtler type is embodied emissions, which is the one-time emissions cost to manufacture the hardware and data center building itself. Using some data at Azure, we find that the breakdown between the two is roughly 50-50. Going one level deeper, we find that compute servers, as opposed to storage or networking servers, cause up to 70% of operational and 40% of embodied emissions. Therefore, we conclude that to reduce the emissions of both types of emissions, we must lower the emissions of compute servers. So then why are compute servers carbon inefficient today? Well, one reason we find is that compute servers are often underutilized. In that if we look at a resource such as CPU, we find that some amount of it on average on a server is allocated to virtual machines, but then a small portion of this is actually utilized. And this also holds for other resources such as memory bandwidth. And so what this points out is that if we consistently design for ever-increasing performance, we lose out on potential carbon savings. And so what we find is that by taking advantage of this underutilization, there are opportunities to design lower carbon compute servers, or what we call green SKUs, where a SKU is a stock keeping unit, or think of it like a server design. So then what are the opportunities for designing these green SKUs, and why should we do this now? Well, we find that there's a recent availability of lower carbon compute server components, such as efficient CPUs, where instead of having what we traditionally use in the orange, where the cores are high performant, large, and power hungry, we can opt for cores that are smaller and more energy efficient, and thus primarily save on operational emissions. And we can see that vendors such as AMD, Intel, and Ampere have all made recently such offerings available. Beyond operational emissions, though, there are also carbon optimizations to lower embodied emissions, such as extending the lifetime of DRAM by reusing DIMMs from decommissioned servers and attaching them via Compute Express Link, or CXL, which allows for backwards compatibility. And this method of reusing server components to avoid the manufacturing cost of newer components can also be extended towards SSDs by taking advantage of PCIe's backwards compatibility. And so this all points out is that there's a recent availability of these lower carbon compute server components that we can take advantage of. But we can't just naively deploy green SKUs because there are practical challenges with doing this at scale. One prime example is that using these lower carbon components, applications may not be able to achieve their performance goals in the cloud. Just to illustrate this, some user might be running an application in the cloud and be offered two options. One is the traditional offering with a high performance core, and another is a green SKU offering from the cloud that uses an efficient CPU, which is lower performance. And while the user might want to save carbon, they may not be able to meet performance goals using the green offering, and thus may not actually opt to use it. And so what this means for a cloud deployment is that most of the servers will need to contain these high performance cores, and this limits the practical carbon savings of a green SKU. And so what this points out is that even once a green SKU is designed, we still need a systematic way to understand if deploying it is worth it. And so this takes us to our contributions, where what I'll first show you is a real green SKU that we designed and built. Then in order to understand its practical potential to save carbon at scale, we developed a framework that does this. And then implementing this framework, we then perform a carbon evaluation of our green SKU. Okay, so starting with our server design. So we leveraged the lower carbon components that I mentioned previously. And here is a photo of the server once built. And it contains an efficient CPU, so specifically AMD's Bergamo CPU, as well as we attach decommissioned DDR4 DIMMs via CXL, as well as reused SSD. And so once built, again, we needed to understand prior to deployment how much carbon could we save, and so this takes us to our framework, where our framework takes as input a green SKU design, and at the output, it tells us the number of green SKUs that we can deploy within a data center. And it achieves this through a number of components. And I know there's a lot going on here. I don't want you to get too bogged down in the details. Just know that each component factors in a practical constraint that limits the number of green SKUs we can deploy within a data center. But as a reminder, what we want at the end of the day is data center level carbon savings. And so to get this, we develop an open source carbon model that translates this number of green SKUs into this final output of the data center carbon savings. And so for the sake of this presentation, I'm going to focus on two components in particular, which the framework uses to answer the question of how server level performance impacts cluster level adoption, where adoption just captures which applications are suitable to run on a green SKU. And so to answer this, we must first answer how do we actually measure a green SKU's performance? And so to do this, let's return to the example we had previously, where some application, and let's use Zapier here as an example, which is an open source search index. And Zapier currently runs in the cloud on a baseline SKU, where we define a baseline SKU as a currently deployed SKU without the green SKU set of optimizations. And so because it currently runs on it, we can assume that with the baseline SKU, it's achieving its performance goals. And what we want to answer is that if Zapier now runs on a green SKU, will it still be able to meet its performance goals? And so to answer this, we must first quantitatively find what is this performance goal. And so to do this, we look at the performance metric of note for Zapier, and since it's an online service, we look at tail latency, where lower is better here. And on the x-axis, we sweep across different loads in queries per second. And so we can first look at the performance of Zapier on the baseline SKU on a nominal set of cores, here 8 cores. And we can then get a service level objective, or SLO, which defines some tail latency that needs to be met at some load. And so with the performance goal in hand, we can then see if Zapier can meet this on the green SKU. And so we run Zapier on the green SKU using the same number of cores, and here we see it does not meet the SLO. But then what we do is we scale up the number of cores on the green SKU until it is able to meet the SLO. So at 10 cores, we're now able to meet the SLO. And so what we find is we're able to determine the number of green SKU cores, in this case an additional 25%, that are needed to achieve the baseline SKU's performance. But again, performance is only one aspect. We need to see if we're saving carbon, even if now we're scaling up resources. So this is where the adoption component comes into play, where it takes the output from the performance component, which is this number of green SKU cores needed, and from our carbon model, we can get the amount of carbon emitted per green SKU core. Multiplying these together, we can get the green SKU's application carbon, which is a measure of how much carbon are we emitting by running Zapier on the green SKU. We can then calculate the same value for the baseline SKU, which allows us to compare the two. And if we find that the green SKU saves carbon, we can say that Zapier should adopt the green SKU because we're meeting performance goals and we're saving carbon. However, if this is not the case, then Zapier should not adopt the green SKU and run the baseline SKU as usual. And so what we find is that we run an application on the green SKU if it saves carbon and meets performance goals. But Zapier is only one application, so we repeat this process across a set of Azure's applications, as shown here, to gain a more representative view of cluster-wide adoption. But again, there's so much more that goes into understanding a green SKU's practical deployment potential. And for much more thorough details, I urge you to see the paper. But just know that taken all together, the framework produces this final output of the data center carbon savings for a given green SKU. And with this output, we can then go about evaluating the carbon savings of the green SKU I showed earlier. And we actually evaluate 2 different green SKU designs to understand design trade-offs. The first is a green SKU efficient design, which contains an efficient CPU, along with new DRAM and new SSD. So this design mainly targets lowering operational emissions. The second design we look at is a green SKU full design with, along with the efficient CPU, it includes reused DRAM and reused SSD. So this design primarily targets lowering embodied emissions. So taking the output from the framework, we can then plot this on the y-axis, where higher is better. And on the x-axis, we sweep across different carbon intensities, which is a measure of how green an energy source is, where on the left, energy is greener, and thus emissions are more embodied dominated. While on the right, energy is less green, and thus emissions are more operational dominated. And so looking at the efficient design, we can see that in more operational dominated scenarios, it performs well because it mainly targets lowering operational emissions. But when we introduce reuse with the full design, we can see that it performs very well in embody-dominated cases and worse in operational-dominated cases because we find that by using older components, this could lead to less energy efficiency. But looking at some real carbon intensity values, in an Azure region with low carbon intensity, we find that reuse is highly effective. But in a region with higher carbon intensity, we find that reuse can potentially backfire. And so this takes us to the first takeaway that different green SKUs are optimal under different conditions. And this highlights this careful trade-off space that needs to be explored where different components trade off operational and embodied emissions differently. But looking at the Azure average, we find that our green SKU is able to save 15% cluster-wide savings at Azure, which is a significant amount. And if we consider the massive scale and growth of cloud computing, could mean carbon savings that are significant even on a global scale. And so just to summarize what I showed you today, I showed you a real green SKU server design and implementation, as well as a framework to evaluate green SKUs' potential to save carbon at scale, as well as we find that green SKUs are potentially a very effective way of reducing emissions at scale. And so while this is what I presented here, there's so much more in the paper that we think will be useful for the community. Just as an example, we provide a comparison against other carbon reduction strategies. But with that, I'd like to first point you all to our artifacts where we make available our carbon model and other pieces of the framework, as well as a link to the paper. And with that, I'd love to take any questions. Thank you.
Questions? No question? Sure.
Hi, Matt Sinclair, Wisconsin. Super interesting talk. If the details are in the paper, that's fine. You can point me to it. But it seemed like the base assumption you were making is there's always some sort of resource in the CPU that can be scaled to make it, the appropriate level of eco-friendly. For example, you're talking about cores. But what if there's not enough parallelism or not enough cache or whatever that resource is that you're scaling to do so? Do you just fall back to the not eco-friendly approach then, or do you just say that's not possible? How do you handle that?
Yeah, so in this case, so you're right that in this case I was showing kind of cores, but we only use cores as kind of like the unit of compute, but we also kind of size up like memory as well as like cache amounts, like in proportion to the core. But if you're considering kind of a case where maybe like it needs a lot of memory and not a lot of compute, then that would probably be reflected in the kind of amount of resources that the VM kind of is allocated in this case.
Oh, okay.
Okay, go ahead.
Oh yeah, Karthik Swaminathan, IBM Research. So I just took a quick look at your paper. I want to know. I was interested in the reliability and maintenance aspect. I think you said you have next to zero overhead due to additional maintenance that would come with these green SKUs. But is there a different, like a test and verification path that you would require for this because of the potentially higher number of errors?
Yeah. So okay, I guess I don't want the screen right now.
Is there an associated overhead to that?
Yeah, I guess, is there, okay. Just give me 1 second here. Sorry, it's in Spanish, so it's hard to, okay, let's see. Okay. So yeah, so we include in the paper, specifically we look at, you're right, so we're potentially extending the lifetimes of DRAM in this case. And so we actually provide a kind of a new study in the paper where we provide this graph. So on the y-axis here, we have failure rates, normalized failure rates, so lower is better in this case. And we look at kind of a group of DIMMs across kind of their age, so their deployment in months on the bottom, and we go up to 7 years, which is kind of well past their normal lifetime. And so as you can see in our case, we see that the actual failure rates, if anything, they decrease, but we don't see a significant increase. And so we actually provide a kind of a model to apply this failure rate and see if we need any extra servers, which might hurt carbon savings in the paper. So yeah, I'd point you there for more details, but we don't see an overhead from this reuse.
So there's no additional testing and verification needed for these SKUs, for these green SKUs, because of because you don't see much degradation.
Yeah, exactly. Yeah.
All right.
Joseph? Actually, Joseph Torellis from Illinois. Same question, really.
Sure.
Are you suggesting reusing used themes and stuff like that?
Yes.
Who's going to be willing to take these things that are, who knows how many years they have been being used without thorough testing or checking that is correct?
Sorry, what was the last part of your question?
That is fully tested, that it is functional.
I see. So I guess going based off of kind of the studies we see in deployment, I think that's kind of the main information that we can use to see if, like, as we extend the lifetimes, if that actually leads to increased failure rates, and we're not seeing that. But if, I guess in terms of testing, you're looking at maybe more kind of device level testing. You're right that if we, in order to kind of safely do this in deployment, I think it would be useful to see kind of more studies like that from kind of hardware vendors. Yeah.
Okay, let's thank the speaker. So we're going to have Owen back, and he's still at UIUC.
Hello, everyone. Now I will present you my work on ECOFAS, rethinking the design of serverless environments for energy efficiency. Serverless computing is an emerging cloud paradigm where users only need to deploy their functions while cloud providers need to provision all the resources. While cloud providers need to provision all the resources required to run such functions. This approach brings many benefits, such as simple and modular programming, automatic resource scaling, and pay-as-you-go billing model. For these reasons, major cloud providers, such as AWS Lambda, Microsoft Azure, Google, and IBM Cloud, they all have serverless offerings. So let's see how serverless computing works. Users need to only deploy their functions to the serverless platform. Then, the platform will store the function in the function database, so where end users want to call the function, they will send the invocation request to the platform, and the platform will fetch the function to the database, and along with the request, send to the load balancer. The load balancer will then pick one of the nodes in the cluster to forward the request to. On every node, there is a node controller that will create all the resources needed to run the function and schedule the function to run on available core. Current research is going towards improving the performance of serverless systems. However, how these performance optimizations reflect to energy efficiency is largely unknown. As serverless computing is becoming more important in the cloud, as cloud and data centers' energy efficiency is skyrocketing, it is crucial to understand how serverless computing as an emerging cloud paradigm affects the energy efficiency. In this work, we perform a characterization of energy efficiency of serverless environments, and based on our observations, we propose ECOFAS, the first energy-efficient serverless system that is based on service-level objectives, or SLOs. ECOFAS reduces the energy consumption of serverless clusters by 42%, while simultaneously reducing the tail latency by 35% over state-of-the-art baselines. So how can we save energy in serverless environments? An obvious approach is to use voltage frequency scaling, or DVFS, and reduce the frequency of our cores, therefore reducing the energy consumption. However, in this work, we observed there are 4 main challenges when using frequency scaling as main energy efficiency knob for getting truly energy efficient serverless environments. First, serverless functions are highly diverse. We take open source functions and execute them at different core frequencies. Here, we show the normalized response time on y-axis and the core frequency on x-axis. We show 2 examples, which are video processing and web server applications. We can see that these 2 functions have very different properties and very different sensitivity to core frequency. To make the matter worse, the end-to-end applications are compositions of multiple functions that can have very different properties. If the users want to reason about how to select the energy optimal execution plan, taking into account the whole end-to-end application, they need to consider the energy performance profiles of each individual function. This creates a large search space that is very difficult to handle by the developers. Instead, we argue that in energy-efficient serverless environments, users should specify only the end-to-end service level objective, or SLO. They do not need to care about the number of cores or frequency of each of these cores. Instead, the serverless platform should automatically and transparently optimize for energy efficiency while making sure that the service level objectives or performance requirements are being met. Once we set the correct core frequency for our functions, we need to take into account that serverless functions are dominated by the idle time. Functions often go to remote storage to fetch data from or to write their results to, and they also call other functions with synchronous RPCs and wait until the results before continuing their execution. In these figures here, you can see the green boxes as the idle time within the functions. However, the existing power management schemes use a run-to-completion model when scheduling the request. This means that they will take a request from the request queue, select the correct core frequency, and then execute until the completion of this request. This includes the significant idle time that this invocation has. Only once the request is completed, the core will start to execute the next invocation from the queue. However, due to the increased queuing delay for this request would need to run at higher frequency, wasting energy. Thus, in energy-efficient serverless environments, we should exploit the abundant idle time to attain the high energy efficiency. However, if we want to naively use this idle time and schedule other ready-to-run invocations, we will lead to a situation where we have frequent context switches, meaning many different functions execute in a core one after another, and these functions can have very different frequency requirements. Thus, on every context switch, we also need to change the core frequency. However, changing the core frequency is very expensive due to software overheads. Therefore, we want to set the correct frequency for every invocation, and we want to use the idle time within invocation so that we can optimize for energy efficiency, but we need to minimize the number of frequency changes if we want to attain high performance. An intuitive approach to do that is to split resources on our server, our cores, into multiple core groups or core pools that run at a given frequency. Then, we can schedule requests to pools that need their frequency. However, serverless workloads are known to be highly dynamic. This means that what is currently optimal organization very quickly can become suboptimal. This means that one of the pools will be overloaded, so we need to run at much higher frequencies and therefore reduce the energy. And also the other pool will be idle, meaning that we will waste CPU cycles. Finally, this means that energy-efficient serverless environments need to dynamically adjust to the fluctuating serverless workloads. Overall, we observe that conventional systems are not optimized for energy efficiency. First, they're not aware, they're oblivious to the performance requirements of our functions, meaning they execute every function on all cores at the highest frequency. This wastes a lot of energy. Second, if we want to apply the existing state-of-the-art power management schemes, they're designed with a run-to-completion model. Therefore, we'll not be able to exploit the abundant idle time within invocations of our functions. And finally, if all the requests share the same queue and same cores on the server, it will lead to frequent context switching across functions, requiring frequent frequency changes, and therefore reducing the throughput of our environment. To address all these challenges, we propose EcoFast, the first energy management framework designed for serverless environments. EcoFast relies on four main ideas. First, it is driven by SLA metrics. In EcoFast, users specify only their end-to-end application workflow, and they specify what is the performance requirement for the whole application. Then, the system automatically and transparently optimizes the execution plan so that it meets the SLA requirements while minimizing the energy consumption. In this example, we have an application with three functions, and we assign a given application SLA for the whole application. Then, this EcoFast will take each function, execute at multiple different frequencies, and measure what is the time to execute the function and what is energy to consume this function. We store information in a delay power table. Then, we use this delay power table along the mixed integer linear programming solver to define what is the optimal deadline for each function within an application. We want to minimize the total energy consumption while ensuring that each function combined together will be below the service level objective for the application. Thus, in the first step, given the application SLA and the application workflow, we get the optimal per function deadlines. Second, we use these profiles to predict the execution time, idle time, and energy to be able to select the correct core frequency for every invocation. Specifically, we use in every function container a specific dispatcher manager that will decide how to run this invocation. When the function arrives along with its assigned deadline, the dispatcher process inside the container will predict what is the execution time, idle time, and energy of this invocation when running at multiple different frequencies. Then it will use the queuing time in existing core pools to determine which core pool will minimize the energy consumption while making sure that this invocation meets its specified deadline. Third, EcoFast splits the cores into frequency classes across server. So in our server, we group the cores into multiple core pools that run always at the same frequency, minimizing the number of core frequency changes. In every core pool, we have a frequency pool scheduler that operates on a shared request queue. In this queue, we have multiple invocations coming from the same or different functions that always need the same frequency. Then the frequency pool scheduler will schedule the invocations on available cores, and once one of the invocations becomes idle, it will select another ready-to-run invocation from the pool. Importantly, we do not need to change frequency even on the context switches because all these functions are already registered to need the same frequency. Finally, Ecofast changes pools and pools frequency dynamically to follow the fluctuating serverless workload. Specifically, we take the node controller or every server that will collect information from each core pool and decide how many cores are needed for each pool and with frequency to run these pools. Core pools will send to the node controller their utilization, which means how many requests they served over time and how many requests could have been served at lower frequency if that such pool existed. Then the node controller will compute how many cores and which frequency is needed for every pool. It will send information and reorganize the cluster accordingly. During the next epoch, our system will operate with this new configuration. To evaluate our system, we use a cluster with 5 Intel Xeon server, and in the paper we have evaluations with a much larger scale. And we use OpenWhisk and K-native platforms. We evaluate 3 different systems, which is baseline state-of-the-art platform from last year ISCA. And on top of that, we add the state-of-the-art power management scheme for monolithic applications, which is Gemini from ISCA'24. And finally, we evaluate our Ecofast proposal. We can see that Ecofast significantly reduces the energy consumption over both baseline and baseline plus power control. By using lower frequencies, by exploiting the idle time within invocations, and by minimizing the frequency changes, we're able to attain high energy efficiency. Compared to state-of-the-art baseline, which is based on plus power control, we can reduce the energy consumption of serverless clusters by 42%. Simultaneously, Ecofast is able to reduce the tail latency of our applications by making sure that we use all the idle time and by minimizing the load imbalance by allowing different functions to share a set of cores. Importantly, we can see that Ecofast also reduces the tail latency slightly over our baseline, which all the time runs at the highest core frequency. Compared to baseline plus power control, we're able to reduce the tail latency by 35%. To conclude, in this work, we observed that serverless computing is very important. It is beneficial for multiple reasons. However, its current execution is very energy inefficient. To make the first step towards truly energy-efficient serverless environments, we propose Ecofast. Ecofast is an SLO-driven, energy-efficient serverless system. It is able to reduce the energy consumption of serverless clusters by 42%, while simultaneously reducing tail latency by 35%. With that, thank you for your attention. I will be happy to take any questions.
Questions? Questions? Yes.
Thanks very much, Reza Azimi from Huawei. You presented 2 papers. I felt that they are sending very different messages, and one of them, or maybe they are complementary, maybe you can comment on that. One of them you're advocating for overclocking. The other one you're saying clock frequency is not the issue. You have to set the, okay, you know, I'm revealing my understanding. You like have core pools with kind of stable clock frequency, and then you do more modeling to assign things to different clock. Can you comment on how they can complement each other?
Thank you. So yes, these are indeed complementary techniques. First, SmartOClock, which was overclocking, is used at high loads when we want to reduce the cost, when we have load spikes, and then we need to operate at either higher frequencies or multiple resources. While when we have lower loads or for functions that are not sensitive to frequencies, then we can lower and use DVFS to reduce even frequency. So combining Ecofast plus SmartOClock, we have much larger scale from going to very low frequencies to overclock frequencies that we can adjust both dynamically to the system load and also to heterogeneity across services and across functions.
I have some follow-up with you.
Yes, thank you.
Akshita Sriraman from Carnegie Mellon. I was wondering, what do you do at the rack level? Because at the rack level, you still have a fixed power budget. So if you're dynamically going to be changing the frequencies of the different pools, do you also have to intelligently figure out which pools need to be located on which racks at what points in time?
Correct. So we assume that every server here can operate with TDP without using the power over subscription. So the rack will be provisioning enough power for every single server. If we want to include power over subscription, then we have limits on the power on the rack level. We would also need then to include a global scheduler that will then determine when to place the functions in the first place, so that we can make sure that the fragmentation, or make sure that these differences across racks will be handled in a uniform way.
That leads me to the question I had, which is a clarification. You said you run a MILP for the load balancer, right?
MILP is used to determine the optimal per function deadlines, which is run only once when we register our application with the system.
But wouldn't that also depend on what it is co-located with and so on? So how do you deal with that issue?
Yeah, so we use the MILP approach just to assign deadlines for functions, assuming a unloaded system. And then we adjust the frequencies in fine grain using these dispatchers within the function containers themselves. So it's determine the deadlines and then obey to deadlines by selecting the right frequency, taking into account the current system state.
Okay. Let's thank the speaker. Thanks everyone. That concludes the session. Have a great evening.